next up, we have Victoria Hunt, data scientist for clean energy team at Intellectual Ventures. And Victoria is presenting simulation of the US electric grid for renewable energy integration. And Victoria, just a reminder to start your timer. Enjoy.
All right, can everybody hear me okay? Okay. Hello everyone, my name is Victoria Hunt and I'm a data scientist. I work for Intellectual Ventures on the clean energy team. And I've been working on the team for about a year now on this project. And I'll be speaking about simulation of the US electric grid for renewable energy integration. About a year ago, when I started working on this project, I actually attended the WIDS conference in person, and I'm really happy to be able to speak at the conference in this new virtual format this year. So my talk will consist of 3 parts. I'm going to give a project overview, and then I'll have 2 vignettes or short examples of different data science problems and how we've addressed them. One is an algorithm for imputing missing data, and one is some examples of how we visualize results from our simulation. And then also a conclusion and how to get more information about our simulation as well as our team, and contact information from me if there's any follow-up questions that I can't get to at the end of the talk. So in a number of talks that I've attended, a number of great interesting talks that I've attended earlier today, there has been a discussion about the business question that's being addressed by the data science algorithms that are being used. And in our case, our business question is a little bit different. We're looking to model for a clean energy future. And the big picture of why we're doing this is because we know that to reduce the negative effects of climate change, it's very important that we reduce our dependence on fossil fuels and we increase our renewable energy for reducing global carbon emissions. In fact, about globally, 2/3 of greenhouse gas emissions are from burning fossil fuels to be used by energy. So to reduce the negative impacts of climate change on human health and weather-related effects, and the other negative effects of climate change, it's very important that we reduce our dependence on fossil fuels. But
Victoria, I'm sorry to interrupt. Your audio is breaking up just a little bit. Can I ask the rest of the panelists just to turn off your video? Sometimes that makes the audio a little weird.
I can also speak a little bit slower if that would help. Is this better?
We'll try it. Yeah, it just seems, it was just breaking up a little.
Okay. Okay, hopefully this is better. Let me know if there are more issues. Okay, so this increasing clean energy is easier said than done. A number of governments have recognized the importance of increasing renewable energy. These include California, for example. They have a very ambitious clean energy goal, and our state of Washington, the state where I am right now as well. However, setting the goal is one thing and how to achieve that goal is another thing. So to understand the challenge to achieve these renewable energy goals, I'm going to give a little bit of background about the US electric grid. So the US electric grid, this is the network that connects generation of energy to the distribution or the demand side where people use energy. So energy is typically not generated at the same exact place where it's used, and the transmission network connects those 2 sides of the equation. The transmission network is a very complex network. You can see a visualization here of all of the branches of this network across the United States. And one important thing to know about energy, electricity, which makes it different than other supplies that you might have, for example, like canned goods. Unlike canned goods, when electricity is generated, it has to be used at the exact instant that it is generated. So the demands must meet the generation at each instant. This this need to meet demands at each instant is very important when we think about the challenges of integrating renewable energy. And this is really one of the main reasons why our team is modeling renewable energy, because we look into the ways that infrastructure might be able to be updated to overcome some of these challenges. Because renewable energy is intermittent and unpredictable relative to other forms of energy, such as fossil fuels, energy that's generated by renewable sources may sometimes be more than what's needed by the demand. And in this case, we have a phenomenon called curtailment. So curtailment is a reduction in the output of generation of what a generator could otherwise produce because it is more than what's needed by the demand. So for example, on this plot on the right side, you can see that there is a time series in the upper right corner. The neon colors are visualization of electricity that is generated by renewable sources that is exceeding demand at a given period of time. And that energy.
Victoria, hi, sorry to interrupt. Your sound is a little bit choppy. I don't know if it's internet speed or anything. Would you try turn off your camera and see if it will help? Thank you very much. Sorry to interrupt.
That's okay. I'm sorry it's choppy.
Actually, now it sounds okay. Yeah, let's see. Thanks.
Okay, I stopped the video. Is this better?
Yeah, so. Actually, it sounds a bit better. Yes. Go keep on. Thank you.
Okay. Sorry for all of the technical challenges. When the electricity is generated by renewable energy, it's exceeding the demand, it will result in something called curtailment, where it will be wasted. And so this is unfortunate. This is something that we want to avoid. It's a challenge of integrating more renewable energy into the U.S. electric system. Our team models paths to overcome these sorts of challenges, and we summarize our findings to support clean energy policy. How do we do that? We have a model that mimics the power system operation. It mimics our system operation hourly segments for an entire year. It can be used to model historic electricity generation for historic years such as 2016, which we consider our base year, or it can be used to simulate a future scenario that we might have interest. For example, a future scenario in which California has greatly increased its renewable energy integration. We use linear programming and we optimize generation dispatch while meeting demand and minimizing cost. As I mentioned before, electricity dispatch generation must always be equal to demand. And then we also incorporate some world limits, such as the transmission capacity and available resources, renewable resources, as well as the generation ramp rate, which means the
Victoria, sorry to interrupt you again. You actually can turn on your camera. I don't think it's the internet speed. Your sound is still cutting off like quite a bit. So I see some suggestions that can you try to see what your input device of your Zoom is in for the mic? It might be your mic's issue.
Okay. You
can turn your camera back on because I don't think it's the internet actually. Sorry about this.
It's okay, I'm sorry. 1 minute.
If you have like a headset or whatnot that you can easily quickly plug in, that would be great too.
I'm now using a headset. Is that better?
Oh, this is actually good. Can you keep talking? Just okay, let's try keep doing it and see.
Okay. Okay. Let me go back.
Sorry. Thank you.
Yes, I'm sorry. Is this better though? The headset?
Yes, I think so. Yeah. So far it's better than before.
Okay. Sorry for all the technical issues. Let me know if it keeps cutting out. So back to where I was, our simulation engine For our modeling efforts, we have a linear programming model where we optimize generation dispatch while meeting demand and minimizing costs at each node. And then we also incorporate some real world limits. I wanted to share with you 2 examples of different data science problems that we address with our modeling efforts. And one of them is imputing missing data. We get data from a variety of sources, including the Energy Information Administration, or EIA, and in some cases, this data is incomplete or has missing sections, or it has sections that are clearly erroneous. And in this case, here you can see a time series of demand data, meaning the energy that is being used at a given location, and you can see that it follows a pattern over time. However, there are some missing sections of this demand data. Those are here. Demand data follows a pattern, and it's highly variable depending on the geographic location, the time of year, the weather pattern, time of day, and then also weekday versus weekend day. So all of these different things can influence the amount of electricity that is used. For example, when it's hot weather, people might be turning on more air conditioners, etc. So the data, while we have a lot of data, the data that is most useful in terms of predicting values of missing data is really the data that is directly adjacent to the missing data section. So what we decided to do, taking this into account and realizing that we couldn't very well use all of our data and use a regression or use predictors to impute the missing data based on our entire body of data, we decided to use the adjacent demand data as best we could to fill in the missing values. And so the way we did that is using pandas data frames for each possible date shift, 1 day forward or 1 day back from the period of time that is missing. And if the data was still missing after that period of time, depending on whether it's a weekend or a weekday, we then look forward 2 days or 2 days back. And we follow these same sorts of rules for 1 week and 1 week back. So we get increasingly more aggressive with how far out we can look. I think this ties in nicely with one of the earlier talks from Aria about how much are we willing to use sort of dirty data. But in this case, it is really important that we fill in and we impute this missing data because we do want to have a very realistic input source of data for demand for our simulations, especially for this historical data. And this shows what happens when we fill in the missing data, use these series of rules and the pandas data frame shift algorithm that I just explained. And so we thought that this performed relatively well. So we were fairly happy with that. It seems to follow the same sort of pattern. However, it's good to be able to check this when we know the correct answer. And so we also did that. So this shows a reality check of how well does this algorithm work when we run the algorithm on a missing section of data that isn't really missing, but that we remove data set and then filled in. And so you can see that the actual data for this period of time and also the data that was filled in using this time shift algorithm are very similar. The other thing that I wanted to share with you was some visualizations. This is something that that is very important to this project because ultimately we have an open source model and we want to be able to widely share our results with policymakers as well as with the general public and to explain what the challenges are of integrating more renewable energy, but also how we may be able to overcome those challenges. So the visuals need to communicate a complex concept, but they also need to be understandable to a general audience. And one of the ways that we do that is by using maps. This is a map showing the congestion of transmission branches of the US grid in the Texas region. And you can see that we've used a color scheme here that's similar to what you might see for a traffic congestion map. This is the kind of map that people are often very familiar with, looking at what the traffic patterns are in a given area. So this is fairly easy to understand at a glance, and it also communicates very well what we want it to, which is that there are certain areas where the transmission will be very congested, meaning that there's electricity flowing over the lines and potentially too much electricity that some of it will ultimately be wasted under that scenario. We also use maps to explain geographic variation in emission reduction that will come about in different future scenarios. So for example, here we have two maps showing generation of carbon emissions in a base case from a past year, 2016. And then looking forward, we use green to show reductions and red to show increases in emissions. So this can show a number of things in a fairly easy to understand manner. The size of the circles indicates the amount of emissions, and then you can also see the size of the circles showing the extent of reduction of those emissions. And you can also see geographic patterns at a glance where you have more natural gas along the coast of California in this example versus more coal inland, etc. We do have a paper with more visualizations and more explanation of our work, and this is available at this citation that's listed here. And I also wanted to highlight this other visualization of demands data over time produced by another member on our team. And I just wanted to also take a minute to thank our very excellent team of researchers. We have a research and policy side with a lot of expertise in the power sector, as well as a software team that helps make this modeling effort all possible. And again, I apologize for the technical glitches. I hope that you were able to hear the last part of my talk, and I thank you very much for attending my talk, and I will go answer some questions if there are any. I also wanted to mention that we are hiring our team as well as the bigger company Intellectual Ventures, and we do have more information, and we have a virtual booth with links to information about those job opportunities.
Yes, thank you, Victoria. And thanks everyone for your patience through the troubleshooting and the suggestions. Victoria, we could definitely hear you much better. So thank you for that. We'll give you all a couple minutes to formulate some questions. I know we've, in the past, we've done a couple questions after the chat. So I'll give you a couple minutes. And if not, we can break.
So I do see one question, and the question is, what kind of background would fit your team? So as I mentioned, we have two sides of our team, although they work very closely together. And we have a research and policy side as well as a software engineering side. For details about the specific requirements for the open positions for our team, I would direct you to that information that's linked to in the virtual booth that we have. But we have a variety of expertise, both software as well as power sector expertise. Okay, the next question is, when dealing with missing data, do you always use the same When dealing with missing data, do you always use the same adjacent method, or do you adjust for different amount of consumption if low consumption, impute, remove, if high consumption, adjacent? So this is one example of one method that we use to impute missing data that we found works for this particular problem, but we do use other algorithms and other methods for other types of data that is missing. A lot of the data science work that I do and that other members of the team do have to do with that cleaning of the data. So it's not always done in this particular way, but this is one method that I wanted to highlight. And then it says, which data visualization tools are you using? They look very nice. Thank you for that compliment. So for these maps that I showed, we are using Bokeh. And personally, I have found that to be a very good tool for this map, for these productions, because it allows you to have some interactivity and to be able to zoom in. There's a number of tools that are in that you can do to highlight and zoom in and do a number of other things, which is good from the perspective of people that might be more interested in a specific region, for example. Okay. Should I continue answering some questions?
Yeah, we've got a couple more minutes. Let's go to 3:50.
Okay. So I see another question. Is this work funded by research grants, or is it funded by selling a product or other? So this work is funded by Bill Gates, and he is very interested in climate change, climate action work. And so this is funded through that. It is not funded by selling a product. And in fact, this is an open source model, and all of our results will also be open source. And the goal is to share this information to help support clean energy policy. Okay. And then I think the last question, does Ivy work with other smart grid companies? So speaking about our team, we work with another, we partner with other entities. So I'm not sure exactly what the question is referring to, but we do have a variety of partnerships that we develop, and academic and otherwise. And then I think this last question is regarding if there is access to the presentation, and I can make this presentation available if that's of interest.
All right. Thank you, Victoria. Thanks for the great talk. This is the end of Technical Track B. Thank you all for attending. We're going to have a 15-minute break, and after that, please join us back in the general stream for closing remarks and a social mixer. There will be many raffles in the mixer round, so please make sure you attend. And thank you all.